Hi, in this video, we want to take a look at imputing missing values with caret. So remember, imputing is where we fill in missing values in our data with a best guess surrogate value to be plugged in. Okay, so the caret package in R is a very powerful machine learning package. This does a lot of stuff for us, and it delivers a lot. You get a lot of bang for your buck with this package. Here we want to talk about the imputation aspects only. All right, so let's think about the situation where I have data that I'm going to build a predictive model on, but I don't have the data that I need to make predictions on yet. Okay, so I get my data in. Let's say I want to predict like Christmas sales, and I have, maybe it's July. I'm going to take last Christmas data. I'm going to build a model to predict how sales will go. And then when I get data, let's say in November, I'll make predictions about the sales. Okay, that's reasonable. Now, most of the imputation software that you will come across cannot actually handle the situation. There are like tons and tons of imputation packages in R that will not tolerate the training portion of the process being separate from the scoring process. So what normally you have to do in, let's say like in mice or in this ranger, you have to take your training data that you use to make a prediction, then you take your prediction data and you put it in one data frame together. Well, that's fine and dandy if you have that data right now, if you have all that you're gonna need. The problem is that maybe you don't have your data. Maybe the data is continuously streaming in and it's not feasible to be building an imputation model every step of the way. So what do you do? Well, fortunately, the caret package handles the situation very nicely because the other functions like mice and Miss Ranger, what they do for imputation is they return a data frame. What the caret package does instead is it takes the data, it will take the data you use for training and then it'll build an imputation model, but it doesn't give you a data frame. It gives you a function that gives you a data frame. So with that function that I get, I take my new scoring data, the data I want to make a prediction on, I put it into that function and I get imputed values. And so I can continuously do this over and over and over. I could have streaming data and this would work out very nicely. Okay, so remember that when I'm building predictive models, I have the data that I'm training, validating, and testing. And then I have the data that I'm going to make a prediction on. These may not come to me at the same time. It might be I have to build the model before I make the predictions, and these have to be time-wise completely separate. All right, so the biggest advantage of the caret package that there is that this handles that situation very easily. The other functions in R, I have not found one that handles this very well at all. Okay, so what we're going to do, we're going to use the preprocess function, and I'm going to put my data in. The preprocess function is going to take the data and give us another function that does the actual imputation for us in the future. Unfortunately, the caret package only handles numeric values. So if I have categorical or factor or character data that has missing values, I have to handle that in a more specific, more special manner. Something that we can do, fortunately, is if I have binary level data, let's say male, female, smoker, non-smoker, yes, no data, then I can convert that to zeros and ones, and then the caret package can impute that. Now, if I have zeros and ones and the imputation gives me like 0.8, then we can view that as a like estimated likelihood of yes being 0.8, estimated likelihood of being a smoker as 0.8. All right, so for the example, let's go ahead and load the data. So we're going to use the snoring data from the Miss MDA package. All right, so I snore, just letting you know, it's been a complaint my entire romantic life. So, you know, as you look through the model, ask yourself, does this fit Dr. Smith? Let's see what aspects are on here. Now, Snoring is a target variable, yes or no. So when I build my model, I'm going to go ahead and use logistic regression at the end of the video. All the other data are predictor data, is predictor variables in this data set. So first and foremost, just to make things a little bit easier to read in the video, I'm going to set digits equal to 2. So I'm rounding off to 2 or 3 decimal places depending on the output. Then I'm loading the data from the MDA package, and it is the snore NA. Remember, that's non-available. NA is what we represent missing values in R. So snore missing values, you can think of it. And now let's go ahead and look at the summary of the data, just to get a feel for what's going on. Specifically, let's look at the missing values. So I have missing values on age, weight, size, alcohol, sex, snore, yes or no, and tobacco. Okay, so this is numeric, 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 numeric. Now here, this is categorical data with 2 levels. This is categorical data with 2 levels, so I can use logistic regression on this. And then this is categorical data with 2 levels. So what I'm going to do in my data preparation, I'm going to convert sex and tobacco to binary variables. And that way I can, binary as in 0 and 1, that way I can impute. Okay, so how the caret package likes to perform is it likes to have your predictor variables separate from your target variable. So here I'm going to say capital X is my collection of predictor variables, and I'm going to say lowercase y is my target variable. Now, technically in the caret package, I could use a formula throughout the process, but in general, the caret package runs better when you split them up. And that's true for a lot of things in R, by the way. Now I'm going to go ahead and make a missing value pattern matrix. And here I'm just using is in A for the missing values. Notice that I'm not making missing value patterns for the target variable. We do not impute target variables. And then, so on this step, when I get my missing values, this is a logical data frame. And I don't want a logical data frame. I want binary. I want 0s and 1s. So this step goes through each column, and it converts each of the columns to a numeric 0 or 1. 1 if it's true, 0 if it is false. And then I go ahead and I take a look, or I put MVP on the column names across each column. That way, when I look at it, I remember, hey, this is the missing value pattern. Now, as I was working through this, I created the missing value pattern, and this is very similar to how things go in real life when you're working on a project. I made my missing value patterns, I started exploring the data, and I went, hey, most of the columns don't have very many missing values. If I don't have very many missing values, then really there's not that much variance in the vector. Therefore, basically all of these vectors are so sparse that they're not going to be very good as predictors. How do I see that? Well, if I look at the row sums, if I add up all of the missing values for each observation, we can see that over 70% have no missing values at all. We can see that 20-something% have exactly 1 missing value, and less than 10% have exactly 2 missing values. Okay, so here there isn't a whole lot of variance off of this. So what I decided to do, you know what, I'm going to make my missing value pattern as just 1 column, where if the observation has 1 or more missing values, it's a 1. If it has no missing values, it's a 0. Okay, so a binary vector. So all of the observations that are in this bar and are in this bar will be a 1 on my missing value pattern. All the ones in all the observations with no missing values at all will be a 0 in my missing value pattern. So here I took the row sums. If the row sum is greater than 0, then I'm going to have a 1 in the vector and a 0 otherwise. Now, I know that sex is a binary, it's a 2-level factor. So what I'm going to do, I'm going to convert it to logical. So I'm saying that if it's for sex, if I have W, a woman, then it's going to be a 1. So the as numeric converts a logical statement to a 1 if it's a woman, 0 if it's a man. A missing value will be left as NA because there's no way for as numeric to convert a missing value to a number. And then tobacco, the tobacco column gets converted to a logical if yes, they are a tobacco user. So yes, if they use tobacco, or sorry, true if they use tobacco, false if they do not. And then we convert it to a 0 or a 1 here. All right, so these three columns are binary 0, 1 vectors, and they're in my predictor set. All right, so now let's go ahead and take a look at actually imputing the values. Oh, this did not print up as nicely as I'd liked. All right, well, I'll fix that for the posting in web courses. So in the preprocess function in caret, we have three options. We have k nearest neighbors, we have bagged trees imputation, and we have median univariate imputation. So with k nearest neighbors, here we're using nearest neighbor model. Now this makes one model for all predictors for imputation. So this is nice. If I have a lot of variables for imputation, this creates one model and it's pretty fast. It works very well. If I use other model-based techniques, it can take a while because each column gets its own model. One disadvantage of k nearest neighbors is that it centers and scales all the predictors. So if you are not planning on using centered and scaled data for predictors, then you do not want to use this technique. I don't see any way around the center and scaling, by the way. And for k nearest neighbors, it is best practice to center and scale or control the range in some manner. I think it should have been optional, but this is what we've got to work with. And one thing that I've had problems with for this technique is that if we have columns with the same missing pattern, it tends to not work for us for imputation. So if my missing value patterns are repeated across different columns, which can vary, that's a very common occurrence when I have different data sources, this method will not work. Now, bag imputation, what this does, this takes bag regression trees to perform the imputation. So what this does, each individual column for imputation gets its own forest of decision trees. And then basically the average of the decision trees for that column is how they determine the actual value for imputation. So I feel that overall this is the best way to go because number one, it does not change my predictor value, so I don't have to worry about center and scaling. And this, I feel like this gives pretty good imputations. I've not had problems with the values that it returns back. A major disadvantage is that this can take a while to compute. If it takes too long to impute, I might not be able to use it because I've got deadlines that I have to work with. Now, median imputation is basically, it just goes through each of the numeric columns and it spits back the median value. All right, so for like binary values, 0 and 1s, or anytime I just have two values, what this is going to give me, unless there's like an even 0.5 situation, this will usually give me the mode of the observations. This is very fast. It does not depend on other columns, so that's an advantage, but this does change the distribution of our columns when we do this. There's advantages and disadvantages with every imputation technique. Based off of your situation, you need to decide what's best. I try to stick with the bag imputation for most of my work. If I was going to center and scale anyway, I didn't have problems with missing value patterns, I would use k nearest neighbors as like my second choice, such as when I have computation time issues with bag imputation. All right, so now let's go ahead and actually build these functions. All right, now this is not the fastest way I could have written this code. There's a slicker ways with lapply, but I'm just going to put things into a list so that we can see things this way. So here I'm calling the preprocess function. I'm passing the data to be imputed. You notice that there are no extra columns in here. This is going to process every single column that I give it. and I'm going to use the method of k nearest neighbor imputation. And I'm going to store that in the list with the name knn impute. Now I do the same thing with bag imputation and median imputation. All right, so now let's look at what we get back. What we're going to get back are 3 different functions, each that imputes the data frame, and they each use a different technique. All right, so first thing I want you to notice is that it's centered and scaled all the variables for k nearest neighbor imputation. And there were 5 that had missing values that went ahead and imputed. Well, how many, oh, sorry, did 5 nearest neighbors for all 7 columns. Okay. Now, what will happen if you try to pass a factor or a character column? It will just ignore it. It won't touch it. It won't change anything. So if I wanted to use this, I could do, I definitely could use this on a data frame using that contained factors in there, but the caret package will just skip over those columns, giving me nothing back in return. If I'm in the situation where I have factors, I have characters, and I can't convert it to binary or numeric in some manner, then what I need to do, I need to use a different function, such as misranger or mice, which comes along with other advantages and disadvantages. Now for bag imputation, we notice that there's no center or scaling here at all. But once again, if I had a factor, if I had a character column, then those columns would be in the ignored group. And the median imputation, same deal. All right, so now let's actually impute the values. Now this step is actually where you get to see that this is why there is such a huge advantage in the caret package. Because when I do the imputation, what I'm doing, I'm taking the predict function, I'm passing my imputation function, and I'm passing the data set. Now this could be any data set with the same columns. So now I need to have the same 7 columns name-wise, and I need to have relatively similar values on there. So I need them all to be numeric. As long as I have those properties in the data set, the predict function will go through and return a data frame with no missing values for me. And so here, same thing. I'm just taking the bag impute function, and I'm telling R to impute the data that has missing values. And for median imputation, same thing. Now on this step, I can have a data frame with any columns I possibly want. In fact, I could take the original data set and pass it into here. It wouldn't give me any problems at all. So you'll notice that the X matrix does not have the snoring data in there. If I wanted to, I could actually take the original data that did include snore, pass it in there, and the caret package will be fine and dandy with it. All I have to do is just give it the same columns, same data type, and it's going to run. Now, if there's anything different about the format, let's say a different range, different center, different scaling aspect, I can have problems, but this will just grab it and run the imputation for me automatically. All right, so now let's go ahead and take a look at what we get back. So here, if I look at the imputed values, so there's over 100 variables, or sorry, over 100 observations, 7 columns to each of these 3 data frames. And I can look through here and I notice I don't have any missing values. Now, if I scroll down a little bit, we can see that when I do bag imputation, once again, we get data with no missing values. And with mean imputation, we have no missing values. Now, let's take a look at the values we get back. All right, so age, we go from 23 to 74. All right, those agree. Median is 51. Median is 51. Mean is 52. Mean is 52. All right, pretty close. And I can go through. I notice that things are pretty close together between bagging imputation and median imputation. There's a little bit of difference if I was to pick through. Like here, the mean is 0.68. Here, the mean is 0.66. But it's not a huge difference, relatively close. These are different functions. But now let's look at k nearest neighbors imputation from negative 2.5 to 1.9, negative 2.6 or 2.7 to 1.6. I mean, these are very different range of values than I had for bag imputation, for I had median imputation. So what's going on is because of the center and scaling, subtracting off the mean, dividing by a standard deviation, everything, all of these columns are normalized. And that's a very important step in a lot of modeling. But if I didn't want that to happen, I have a problem, because now I have a different range of data than what I actually want. All right, so I played around with the models before making the video, and to improve the models, I went ahead and I did variable selection. So I did backwards elimination. I started with a full model, and I removed MVP, and then I removed weight, size, sex, then tobacco. This is the order that I removed them in, and I just went through and removed them. So what this step does, this goes through my imputation value, imputated data matrices, and I kick them out. I kick out the variables I don't want. Now let's go ahead and actually build our models. So here, what I'm going to do, I'm going to use the train function in caret. This is the workhorse of the caret package. I'm going to take my imputed data, I'm going to put it into the train function. I'm going to do generalized linear model, so I'm doing logistic regression. And I choose to do repeated cross-validation. I'm going to do twofold cross-validation. I'm going to repeat it 10 times. All right, I like twofold cross-validation. Why do I like this? Well, if you think about it, if I split my data in two, I have two sets. This one is my train set, this is validation, but I go both ways. The other way, this one is a train, this one is a validation. I do a 50-50 split on my data. I like this because my train sets are completely independent of each other. I have no overlap between my data. I feel like this is a better way of evaluating model fit. Now, a disadvantage of this is that I'm not using all my data in this. So one thing I do to compensate is I repeat the process 5 or 10 times to give me kind of like a distribution of values, give me more insight into what's going on. Now here I'm going to do the same thing. Now you will notice that the code for this is completely the same as what I had for the previous chunk, but I'm doing bag imputation, or the bag imputed data set instead of the k nearest neighbor. So the only difference between this chunk of code and the previous chunk of code is the data that I'm passing. I'm using the same model, I'm using the same validation technique, and I'm using the same number of splits, I'm using the same number of repetitions. So that really the only major difference between these two model building sessions is the data that I'm using. I'm using the same model structure, the same validation technique. Oh, and this is complaining about the missing values in the target variable, and it does not cause any problems for the output. And then here I'm going to go ahead and use the data that was imputed using median imputation, and then I'm going to run with that. So I've got the same model structure, same validation technique. The only difference is that I'm using different data. So let's compare the models. All right, so with k nearest neighbor, we have an accuracy of 0.66. It's not really great, honestly, but whatever. For bag imputation, we have 0.67. So off our cross-validation, we can see that bag imputation is slightly better. And then median imputation, 0.67. So we're not seeing a huge advantage of using bag imputation or k nearest neighbors. I looked previously, and because of rounding, median imputation looks exactly equal to bag imputation. Bag imputation was just a little bit better, but not very much. Now, something to consider when I look at this, if I look at the original data, when I look at snoring, no is 62%, and yes is 32. So I could hit a 62% accuracy just by saying no to everything. So that shows that really I'm not using very good models, honestly. But the point of this video is to show you the process, not how we tune and improve our data, our models. The goal here is just for you to see, how do I impute values? All right, so here I would use bag imputation if I had to. Here is the final model for k-nearest neighbor imputation. And now remember that I have a different scaled predictor variables. So when I look at these coefficients, I need to interpret them differently than here. So let's look at the bag imputation and median imputation coefficients. All right, so here the intercept is about -5. When I look down here, I see it's about -5. Age coefficient is about 0.07. Here, the age coefficient is about 0.07. The alcohol coefficient is about 0.2. The alcohol coefficient is about 0.2. So I expect that the model would be something around -0.5 with a coefficient of 0.07 for age and a coefficient of alcohol around 0.2. I might go ahead and just use those coefficients, those simpler ones. That way, when I go through to explain to decision makers what I have, I'm just going with an easier model. Now, here, I'm not considering interactions. I'm not considering transforms on the predictors. There are plenty of ways I could improve this model, but for now, we're just going to look at things a little bit easier. Now, something that you'll notice when I go up to the k-nearest neighbors output, remember that things were scaled, right? Center and scaled. You'll notice that the standard error for each of the coefficients, they're all pretty close to each other. Now, age is probably collinear with the other two. You see that it's the biggest, but there might be a little bit of collinearity going on, but I mean, it's really, really tiny in this situation. I wouldn't worry about it too much. All my predictors are statistically significant. Also, my number of iterations is pretty small. A good rule of thumb is if it takes a lot of iterations for a model to converge, you probably have bad model structure. So that's just something to give you a heads up as you work through problems. When I look down here, remember I did not center and scale my predictor variables. And so the standard error is just all over the place. So one of the reasons why center and scaling is nice is that the coefficients are a little bit easier to interpret in terms of like z-values. Here, it's because we're dividing by a standard error to get the z-value, and things are closer to consistent, there's more of a consistency between the coefficient value and the z-score. All right, well, that's all I've got for you. Take care and goodbye.